Hey there, chemistry team! It's your chemistry coach coming at you with some more pain and punishment for your brain. Boot camp for the brain, baby. All right, we have an issue here. If we look at redox reactions, if they're not in solution, not so bad, right? You can predict your products pretty easily. If it's not possible, I'm sure your professor will give them to you at that point, depending what level you're at. And you can usually balance those by inspection, just by looking at it like you've been doing since introductory chemistry. But if you're in solution, you've got species, a lot of times polyatomic ions, some weird stuff you've probably never seen before with a little AQ after there. Predicting your products, either they're given, most of the time they're given to you, but if not, you can use that redox table in the other video to predict what those products are. But you got to know whether you're in acidic or basic solution, right? Balancing, pain in the butt. All right, don't even try to balance those by inspection. Not going to happen. If it's an aqueous solution, we're going to have to take this overly complicated reaction, break it down into its component parts, into simpler parts. I'm going to take this, break it apart, balance this part, which is simpler, and I can do that, balance this part, which is simpler, and then recombine. The process we're going to use at this level is the half reaction method. If you move, once you really understand this, and you feel pretty good at it, because this is kind of bulky and tedious, but it shows your professor and that you know what you're doing. And it's easier to grade and give partial credit as well, because it shows all the unique individual steps. So it takes a while, but if you make a mistake, which is very possible, right? Got electrons flying all over the place. It's easy for the professor to find where that mistake happened and then track if your thinking process is correct. If you do the bar method, which is kind of the shortcut to this, yeah, you either get it right or wrong. It's pretty tough to tell where your mistakes were made. So this is what we're going to be doing at this point. If you're at a higher level and you feel pretty confident and you want to go to the bar method, go for it. Nice and quick. All right. For balancing reactions in redox reactions in solution, this is in essence what we're going to do. And depending what textbook you're using, what professor you have, you might get a different style. I've seen 3 or 4 different ways to approach this. Hey. Right? And also it depends whether you use the H plus ion as a shortcut representation of the actual hydronium ion, H3O plus. So for us, we're going to use hydronium ions. So the processes that we're going to use to balance this using the half reaction method. So if you go on my website, you can print this out. We're going to follow these 11 steps here. Download that on your phone. This is also in your laboratory notebook, your general chemistry notes, with a little more detail on there. But I'll provide you that on exams. You don't have to memorize the steps, although if you do this enough, you won't need that. So we're going to be using H3O plus instead of H plus. All right, so first we need to know, is this an acidic solution or basic solution? Because that'll determine what products you form, and how we balance one of our specific steps, how we balance things will be dependent on whether it's a basic solution or acidic solution. So that has to be stated in the problem or be intuitively obvious from the reactants. If you look at the redox table, you can see they both have to be in the A medium, acidic medium, or both have to be in the B or basic medium. That you might be able to determine, so maybe it's not provided for you specifically it's acidic or basic, but you could probably deduce it from the redox table. But more often than not, especially with your homeworks, it will be stated, balance this in basic solution, balance the following in acidic solution. Okay, that's pretty obvious. If you're on an exam or quiz and it's not clear to you, just raise your hand, right? And I'll come by and say, oh, crap, I forgot to tell you. Everybody, make a note. And then you're like, ah, whatever. Or I'll be, well, I gave you some hints on how to do that. You should be able to figure that out. Once you know if it's acidic or basic solution, predict your products. If not provided, a lot of times they'll provide it for you, especially if the point's just to balance it, especially for reactions that really wouldn't happen spontaneously on their own. Theoretically ain't going to happen in lab, but we can theoretically balance it. Then what we're going to do is we're going to take this complicated overall equation or reaction that we can't balance by inspection, and we're going to break it up into 2 parts. The half where oxidation occurs and the half where reduction occurs. Remember, oxidation is giving off electrons, reduction is gaining electrons. We're going to split them up. Then what we're going to do is balance the oxidation half reaction by itself, because it's more simplistic, using those 11 steps. And then we're going to balance the reduction half reaction by itself because we can do it. It's simplified. And once we've balanced those and we're happy with those two half parts, those half reactions, that's why it's called the half reaction method. Right? Balance the half reactions separately. Once we're done, make sure when we recombine them, the electrons cancel out, right? The whole point is the number of electrons transferred, number of electrons given off, and the number of electrons taken has to be the same. Can't have electrons floating around doing nothing or coming from nowhere. Like my English there. So we're going to balance the electrons transferred, recombine them, and then we'll simplify. We'll see things on both sides of the arrow that can cancel out. The electrons should cancel out. Usually some waters or stuff cancel out. Let's do one example in basic solution. Let's do one example in acidic solution so we can walk through the steps together. But make sure that you have this with you. The half reaction steps. Again, depending what textbook you're using, you probably won't use this. You'll probably use a different technique. You still get the same answer. And if your professor prefers H+, use that. If they prefer H3O+, use that. All right? Here we go. Let me write a problem up on the board. All right, so we used this particular reaction in the prior video on how to use redox tables to predict products. So sometimes the products are provided, sometimes they're not. But step one, you got to know on an exam, is it acidic or basic? Balance in basic solution, ding, 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 ding. We're a winner, we're in basic solution. That's going to affect how we balance this, okay? And it's going to affect how we predict our products. Again, you go, oh, you poopy head, man. Professor didn't give me the products. What a booger. So you pull out your trusty redox table. If you don't remember how to use this, review the last video. But what you do is you look up and you find the permanganate ion here, and you find the permanganate ion there. This one's in basic solution. This one's in acidic solution. All right, so you got, that's why you have to know if it's acidic or basic. You might get different products. So this is in basic solution. So we're going to find the permanganate down here in basic solution, which gives us MnO2. That'll be a solid. So product number one will be MnO2. So let's write that down. And then product number two, let's find as a reducer the sulfite right there. See how the arrow points to the sulfate? As long as it's not acidic, right? So basic would qualify as not acidic. So we're going to get the sulfate ion. So sulfite becomes sulfate. And anything with a charge has to be AQ. So now we predicted our products. And again, sometimes that's provided for you. And this will be our oxidizer. And this will be our reducer right here. So this is our oxidizer. And this is our reducer or reducing agent based on the table. So electrons are going to be going from the oxidizer, from the reducer to the oxidizer, right? So that'll cause that to be reduced. That'll cause that to be oxidized. Let's walk through the steps together. So step one, label your oxidation numbers and label your electron transfer for that reaction. This is our electron accounting, right? So we got to figure out what all, and if you're rusty on your oxidation numbers, brush up on it now. Here we go. Let's take a look at our oxidation numbers. Oxygen's always assigned a -2, all right? So if that's a -2, and there's 4 of them, that's -8. So what -8 gives me -1. The manganese in the permanganate must be a +7, all right? We're in the sulfite ion. We're going to assign each oxygen atom as a -2. So what, there's 3 of them, right? So what -6 gives me a -2. All right, so that should be a +4. 4 minus 6 is -2. Over here, we're going to assign the oxygen a -2. We're always going to do that in a compound unless it's a peroxide. And that's neutral, so there's 2 of them. So what -4 is 0, right? So the manganese must be a +4 there. Over here, we're going to assign the oxygen. Are you seeing a pattern here? The oxygen is a -2. So what, and there's 4 of them, so that 4 times -2 is -8. So what -8 is -2? So that must be a +6. That is step 1. Label the oxidation numbers. If you screw that up, it snowballs into a very bad day for you. And you'll waste 15 minutes on the test going, I don't know, tears streaming down, what just happened? And you just waste it all. Just weep a little bit, stop, finish the rest of the test, and then come back later. Because there's odds are you could waste another 10 minutes not know what the heck just happened. Let's label our electron transfer. So we're going to use some arrows to connect the reduction part to the oxidation part. Now, would you agree the manganese is going from a +7 to a +4? So the manganese is being reduced. So let's connect those two together. Now, to get from 7 to 4, it would have to gain 3 electrons. So I'm going to go +3 electrons reduction. Okay, to go from a 7 to a 4. That means that the sulfur is going from a 4 to a 6. It's going up. All right, so it's losing 2 electrons. So one must go up, one must go down. If you get 2 going up or 2 going down, something bad happened. So let's connect these babies together. I'm going to connect the sulfur here to the sulfur there. So to go from 4 to 6, it's losing 2 electrons. And there's my oxidation. All right. This is going to take a while, so I might need to do the next example on another video. We'll see. But these can take a while, especially when you're explaining it the first time. I got to explain every single step. The more you do this, the faster you get at it. All right, we have finished step 2. Now step 3, we're going to write the half reactions, including the electrons. So this is when we're going to split this up. We're going to split it up. So I'm going to take this, and I'm going to write my oxidation half reaction. And I'm going to end up balancing these on separate boards, but I'll write the 2 half reactions right now. So let's see. So this is oxidized. So let's do our oxidation half reaction. That will be the MnO4 minus the permanganate. And that's going to MnO2 but going from 7 to 4, it's gaining 3 electrons, right? So we need to add those 3 electrons. That's what we mean by including electrons in a oxide. Oh boy, I got them on the wrong side there. That wouldn't make any sense. This is the reduction half reaction. You guys need to correct me when I make mistakes like that. This is the reduction half reaction. Must be early in the morning because it's going down. That would be reduction. All right? So if I didn't realize that, I would have caught it pretty quick. So when you're reducing something, you're gaining electrons, right? So it's going from a 7 to a 4. So it must be gaining 3 electrons. So in reduction half reactions, the electrons are always on the left-hand side, on the reactant side. Now let's do the oxidation half reaction. That will be the sulfur species, because the sulfur is going from a 4 to a 6. So let's take the sulfur in the sulfite. That is losing 2 electrons. So in oxidation half reactions, the electrons are on the right-hand side, the product side. So that is going to go to the sulfate plus the 2 to go from 4 to 2. It's losing 2. So what I've done is I've split in step 3. I've written the 2 half reactions, including the electrons. I haven't balanced anything yet, but now I can do that. Starting with step 4, I'm going to start balancing these. So what I'll do is I'll do the reduction half reaction on one board. I'll do the oxidation half reaction on another board, and then we'll recombine them. Steps are going to be exactly the same. What I like to do when I have a large piece of paper on my own, I just draw a line down the center of the page. I'll do like either the oxidation or reduction half reaction on the left side, and the other one on the right-hand side. It doesn't matter what order you do them, and it's irrelevant. And then I like to do the steps simultaneously. I'll do step 1, step 2, step 3, and kind of do them both at the same time. Or you could do the reduction first and the oxidation first. It doesn't matter, whatever works for you. So I'm going to erase this. Let's do the reduction half reaction together. All right, let's make life more simplified. Let's focus in here. I'm going to leave the states off, because it just gets redundant. And what we'll do is we'll add states in when we're all done. When we balance them, recombine them, balance the electrons. When we're all done and write the final balanced overall equation, then let's stick the states back in, because it's just kind of tedious and a waste of time and space while we're doing all these steps. You'll appreciate it once we get through. We're going to fill this whole stupid board up. Here we go. Number 4, balance atoms other than oxygen or hydrogen. There's some exceptions to that. If the oxygen or hydrogen is the actual element that's oxidizing or reducing, then we got some issues. I personally won't give that to you on quizzes or exams. Lab and homework's fair game. So those get a little bit tricky, but you can play around with it. But I will keep with things that follow these steps. All right, so balance everything but oxygen and hydrogen, and keep electrons balanced. All right? So we won't see that issue for this problem, but we will for the next one. So I'll explain that when we hit it. We're not going to have it here. Now, I'm not going to worry about balancing the oxygens in this step 4. But the manganese I would, but I have one manganese here and one there, so I'm good. I'm good there, right? So step 4, we're done. Yeah, I'm going to give you that in a test. All right, so everything's balanced other than the oxygen. We just got to figure out how to balance the oxygen. So now step 5, and this is where different textbooks, different professors might have separate approaches. They might mix these steps up a little bit. All right, that's okay. But use the steps that your professor at that moment giving you the grade is giving for you. So step 5, we're going to balance the overall charge. Now, this is where acidic or basic matters. If we're in acidic solution, we're going to use the hydronium ion. A lot of textbooks use H+, but we like the more realistic hydronium ion here. If it's acidic solution, we're going to use the hydronium ion to balance the charge. If it's basic solution, we're going to use the hydroxide ion to balance the charge. Since this is in basic solution, we're going to use the hydroxide ion to balance the charge of this puppy. So let's take a look here. Do you see that this side, I have 1 permanganate ion for a -1 and 3 electrons for a -3. So we have a total of -4 on my reactant side. We good? Over here, this is neutral. Would you agree that those charges don't equal each other? The charge of the reactants total does not equal the charge of the product. So you take the coefficient times the charge of that species. So 1 times -1, 3 times -1 gives you a total of -4. I'm using OH minus because this is in basic solution. So I don't want to add, I'm not going to add it on the left-hand side. That would make it more negative. So I need to add enough hydroxides to the right-hand side so that it equals -4. That would mean I need to add 4 hydroxides to that side. So I'm going to go MnO4 minus plus 3E minus going to MnO2 plus 4OH minus. We did that to balance the charge. All right, so each step is fairly simple, but if you do it out of order, you're toast. All right. If you miss one little electron, you're toast. If you had that as like a 2 or a 4, you'll see it snowballing really bad, like going down a skateboard down a big hill, and you start going like this, and in your brain you're like, I'm going to crash. And you haven't crashed yet, but you know the impending doom is coming. It's that same feeling. You just get a bad feeling in your gut with this going, I'm crashing, and it's just spiraling out of control. And poof, I got some scars from the skateboards to prove that one. All right, so we've successfully balanced these. This side is a -4, all right? And this side is a -4. Happy face, happy face. All right. Now we can go to step 6. Balance the oxygen atoms. Here's where we balance the oxygen atoms. We're going to use liquid water to do that. Use liquid water. So let's take a look at our oxygen atoms. I have 4 oxygen atoms on my reactant side and 4, 5, 6 oxygen atoms on the right-hand side. So I have more on the right, which means I have to add water to the left to do that. And if I have 6 oxygen atoms, 4, 5, 6, so let's write that down. And I have 6 oxygen atoms here and 4 oxygen atoms There, they don't equal each other. So I need 2 more oxygen atoms on the left-hand side, and since a water molecule only has 1, I need to add 2 waters to the left-hand side, my friend. So let's add the 2 waters there, and I'll add states later. You can see how these steps get a little crazy. Let's write this all in. So now I can say, hey, 4, 5, 6 oxygen atoms. 4, 5, 6, 6 oxygen atoms. And the whole point for this was to balance oxygen. You will find that you never actually physically balance the hydrogens. They should work out if you do everything correct. So that's where step 7 comes in. Step 7 is a chance to stop and go, how we doing so far? So in step 7, you'll know whether your guts, you know, am I crashing, about to go splat, scrape some skin on the pavement? You'll know in step 7. So we're going to check the hydrogens. So in step 7, if we did everything right up to this point, the hydrogens should balance. Let's take a look. 2 times 2 is 4, right? So I've got 4 hydrogen atoms. There's none there. 4 times 1 is 4. 4 hydrogen atoms. And on the test, you go, oh, yay! Thank you, chem gods! Thank you, Heisenberg! Now, that's as far as we're going to get, because in step 8, we're going to recombine the 2 half reactions. So what we're going to do is now pull up the oxidation half reaction and do exactly the same thing. So I'm going to erase this, but I'll bring this half reaction back up. But notice we've got 3 electrons on the left-hand side. We have to make sure that we have the same number of electrons on the right-hand side for the oxidation half reaction. If they're not, we're going to have to find the least common multiple to make those the same, so they cancel out when we recombine. The whole point is to cancel the electrons out when we recombine the 2 half reactions. So let's do the oxidation half reaction. All right, challenge yourself and see if you can do this on your own before I do. Let's walk through the steps again. So we did steps 1 and 2. We did step 3. We wrote the half reactions. Now balance all atoms other than oxygen and hydrogen. Don't worry about the oxygens. 1 sulfur, 1 sulfur. Yay! Done with step 4. That's my favorite step. Number 5, balance the overall charge. Since this is in basic solution, we're going to use OH minus like we did last time. So this side has 1 sulfate for a -2. This is a -2 plus 2, so this side's a -4. Those charges aren't equal, so I need to add 2 hydroxides on the left-hand side to get this to -4. Let's do that. Let's add 2 hydroxides to this side, and that will equate our charges together. And now I can safely say, hey, the product side's a -4, the reactant side's a -4. 2 times -1, and 1 times -2. -2 plus -2 is -4. We're good. Let's go to, that's the key, one of the key steps right there, step 5. Step 6, balance the oxygens using water. It's the same process over and over. After you do it enough, you won't need this anymore. Let's take a look at our oxygens. I have 1, 2, 3, 4, 5 oxygen atoms there. And I have 4 oxygen atoms there. Everybody agree? Everybody agree? Everybody agree? I need 1 more oxygen on this side, so I need to add a water to the right-hand side. So we're going to take the 2OH minus plus the sulfite, giving us sulfate plus 2E minus plus 1 water. And now we have 4, 5 oxygen atoms and 5 oxygen atoms. Ha ha ha! So again, this step here, we're balancing the charge using the hydroxides. And here we're balancing the oxygen atoms in step 6. If we did it right in step 7, the hydrogen should balance. Can you see how you're going to get faster and faster the more you do this? First few times you're like, my brain! All right, I have 2 hydrogen atoms here. None, none, 2 hydrogen atoms there. So I've successfully balanced my 2 half reactions. Now what we're going to do is recombine them. So I'm going to erase this board, put up the 2 half reactions, and let's look at the electrons, because that's what step 8's about. We're going to balance the total electrons transferred between the half reactions. We have to make sure they are the same. So we're going to have to multiply these half reactions. See the 2 here? In the reduction half reaction, it was a 3 on this side. 3 does not equal 2, so we're going to have to find the least common multiple of 6 to do this. Let's write them both back up. All right, so I rewrote these back up. Notice the 3 electrons there and the 2 electrons there. Those do not equal each other. So in step 8, we need to make them equal to each other. So the least common multiple between 2 and 3 is 6. So I need to take my oxidation half reaction. 2 times 3 is 6. And I need to take my reduction half reaction, and 3 times 2 is 6. So I'm going to rewrite these equations, and I'm going to multiply everything by 2 in that one and everything by 3 in that one. That's going to take me a while, so I'm going to pause it. You go ahead and do that with me, and then I'll bring this back up again. It's tedious, doable, but tedious. Did you rewrite them? Did you rewrite them? So we're going to take the reduction half reaction, multiply everything by 2, because again, the goal is to cancel the electrons out. So 2 times 2, we now get 4 waters. 2 times 1, we get, whoa, why did I get the Mn2 plus there? That was weird. I was thinking something else. That would have really messed us up. 2 times 3 is 6 electrons. 2 times 1 is 2 MnO2. 2 times 4 is 8 hydroxides. For the oxidation half reaction, we're multiplying everything by 3. So we're going to get 3 times 2 is 6 OH minus. 3 times 1 is 3 sulfites. 3 times 1 is 3 sulfates. 3 times 2 is 6 electrons. 3 times 1 is 3 waters. Notice the 6 electrons, when we recombine them, we'll have 6 electrons on the right and 6 electrons on the left. So rewrite these. Now what I'm going to do is I'm going to take everything on the left-hand side for both half reactions and put them together, and then everything on the right-hand side. So I'm going to take that plus that plus that plus that plus that gives me, arrow, that plus that plus that plus that plus that. I'm going to write that on the next board. That's going to be pretty bulky. And then we're going to cancel out like species on both sides, like having a 2x on one side and a 4x on the other. Subtract 2x from both sides. See if you can do it before I do, and let's polish this off. And we'll do acidic solution in a separate video. All right, did you recombine them? Some of you can skip this step and do it in your head. So I'm going to take everything on the left, the 4 waters, the 2 permanganates, the 6 electrons, the 6 hydroxides, and the 3 sulfites, giving me everything on the right, 2 MnO2s, 8 hydroxides, 3 sulfates, 6 electrons, 3 waters. That's all we're doing. I'm going to put the states in when I simplify this. So what we want to do now is simplify. That's what we're doing on here. So we recombine the half reactions, right, in step 9, and then we're going to simplify the overall equation, and then we'll just double check it. All right, do a quick little double check. Can you see? Can you see what I'm saying? We got 4 waters here and 3 waters there. Everybody agree? That's going to go bye-bye, and that will go to a 1. So we subtract 3 waters from both sides. No permanganates on the right-hand side. The 6 electrons are going to cancel the 6 electrons. So that's the whole point, for those to disappear. You got electrons lingering your toast. We got 6 OH minus there and 8 there. So let's subtract 6 OH minus from both sides. So that goes away, and that goes to a 2. So take a second. I'm going to pause this. You write the overall simplified equation for me real quick. I'll do it myself, and we'll meet in a few seconds. All right, did you get it? So cancel them out. You'll end up with 1 water on the left, 2 permanganates and 3 sulfites, 2 MnO2s on the right, 2 hydroxides and 3 sulfates. Now I insert the states back in, and just double check it. Check the overall charge. Do you see on the product side, that's neutral? That's a 2 minus, 2 times -1, 3 times -2. So I got 6, 7, I got a -8 on my reactant side. Neutral, 2 times 1 is -2, 3 times 2 is -6, -6 and -2. See how the charge is balanced? That's how you know you're good as gold. -8 is -8. Woo! Let's do a harder one now in the next video. Yay us!